Good day, viewers. This is 300 Plus Academy, where all we do is exams tutoring, ensuring that you ace your next exam. Okay, I haven't started with gas laws. We've looked at Boyle's law, Charles' law, and of course, Avogadro's law. It's about time we look at what we call general gas equation, otherwise called equation of states. Otherwise called equation of state. It is a combination of Boyle's law and Charles' law. Recall that Boyle's law states that volume is inversely proportional to pressure. And remember that Charles's law states that volume is directly proportional to temperature. Combining these two, what we're going to have is volume inversely proportional to pressure and volume directly proportional to temperature. Combining this, we have V equals to KT over P. That's this proportionality sign becomes a constant, and then you have your temperature times 1 temperature, and of course pressure, so that what you have is PV over T equals to constant. The T is going to come here, P is going to move here, so PV over T equals to constant. What the constant here represents is the given mass of gas, talking about number of moles. Remember that the 4 parameters we use in describing the behavior of a gas talks about volume, pressure, temperature, and number of moles of gas, or the amount of gas. V, P, and T appears in this equation. The only variable not appearing is N. So for equation of state, our number of moles of gas does not appear, so the constant represents that. Of course, once you have a constant here, it means that P1 V1 over T1 equals to P2 V2 over T2. This, of course, is our equation of state, where we are talking about 3 variables being involved in describing the condition or state of a gas. That said, certain things we need to quickly talk about before we, move into calculation is what we call standard temperature and pressure, STP. When we talk about standard temperature and pressure, you're looking at a unified temperature at which scientists carry out experiments, so that we eliminate, disparity when we carry out the experiment, owing to variations in temperature and pressure in various parts of the world. There are places, with very high pressure. There are places with low pressure. There are places also with very high temperature, and there are places with very low temperature. So to eliminate sources of errors, when it comes to uniformity in the field of science, it has been agreed internationally that experiments be carried out at certain standard temperature and at certain standard pressure. Standard temperature at which scientific experiments are to be carried out is 273 Kelvin or 0 degree Celsius, and standard pressure at which experiments are to be carried out is 760 millimeter mercury, or 1 atmosphere, or what we call 1.01 times 10 raised to the power 5 Newton per meter square. So this is our standard temperature and pressure. It is the temperature at which and pressure at which experiments are carried out in the field of science, so as to encourage uniformity. Also, for equation of state, recall we talked about P1 V1 T1 equals to P2 V2 over T2. There are instances whereby gases are collected over water, most especially gases that are insoluble in water. Take, for example, as in the case of preparation of hydrogen gas. Let's say when zinc is being attacked by hydrochloric acid, this is what we'll have, from equation: zinc chloride plus hydrogen gas. Now, let's assume that in this experiment, we have a flat bottom flask, such that this is our zinc, and then acid is being passed in, using the test tube funnel. Let this be HCl being passed in. Hydrogen gas is going to be liberated here. Hydrogen gas being liberated. And now let's look at situation whereby let this be water. Let's look at situations whereby as the hydrogen gas is being liberated here, the hydrogen gas moves this way, and of course, gets into water. But being that hydrogen gas is insoluble in water, moves in, and the hydrogen gas is collected in the space above the water. You need to understand that there are instances whereby some of the water here will change to the gaseous form of water, so that the total pressure you have here is the pressure of the gas we are talking about, in this case hydrogen, plus the saturated vapor pressure of water. So in calculations involving gases being collected over water, for you to get the pressure of the dry gas, you should be saying pressure of the dry gas, in this case hydrogen, equals the total pressure minus the saturated vapor pressure of water that must have moved along with the gases. This here is the real figure you use in calculations that involves collection of gases over water. So that said, let's quickly move into questions for general gas equation, otherwise known as equation of state. Looking at question 1 here, it says a given mass of gas has a volume of 7.5 dm cube. That is V1 equals to 7.5 dm cube at 250 Kelvin. The temperature T1 here is 250 Kelvin, and the pressure of P1, that's 80 kilonewton per meter square. Calculate the pressure at which it will have a volume of 7.2 dm cube. Okay, V2, 7.2 dm cube, and temperature T2, according to this, is 270 Kelvin. We were told to calculate the pressure, so we're looking for P2, and that's the question. So when you look at it, P1 V1 over T1 equals to P2 V2 over T2. Since we're looking for this, this will move here. So you have P1 V1 T2 divided by T1, and then V2 will come here, and that's why we have P2 equals to this. So in this regard, what you have is P2 equals to, what is P1? 80 kilonewton per meter square times V1 7.5 times T1 times T2, 270, all divided by T1 is 250 times V2 is 7.2. When we compute this, we'll get 90 kilonewton per meter square. If the P1 is in kilonewton per meter square, then the P2 is going to be in kilonewton per meter square as well. Let's look at the second question. A fixed mass of gas has a volume of 440 cm cube. So V1 equals to 440 cm cube. Okay, at 13 degrees Celsius, T1 is 13 degrees Celsius. We must convert to the Kelvin scale, plus 273, and this will give us 286 Kelvin. Okay, and 836 millimeter mercury. P1 here is 836 millimeter mercury. We were told to calculate its volume at standard temperature and pressure. That's STP. Okay, what this means is that we should look for V2. That's the question. at STP. At STP. In this case, you need to understand that our T2 is going to be the standard temperature, and that's 273 Kelvin. Our P2 is going to be the standard pressure, and that is 760 millimeter mercury. So having this, we are looking for V2. When we use P1, V1 over T1 equals to P2, V2 over T2. Since I'm looking for V2, T2 comes here. I'm gonna have P1 V1 over P1 V1 T2 divided by T1 P2, and that is going to mean, okay, equals to V2, and that's going to mean V2 equals to, what is my P1? 836 times, what is my V1? 440 times, what is my T2? T2 here is my standard temperature, that's 273, all divided by, what is my T1? T1 here is 286 times, what is my P2? My P2 is the standard pressure, 760. So that way I'll be able to get the new volume when I compute. V2, when we compute, is going to give us 462 cm cube. That is the volume. But the important thing here is knowing that when you're told to calculate your volume at STP, your standard temperature is 273 Kelvin, and your standard pressure here is 760 millimeter mercury, depending on the sort of pressure that you have for your P1. If this were to be in atmosphere, then you use a standard pressure in atmosphere, and that's 1 atmosphere. So that ends question 2. Question 3 states, calculate the final pressure of a gas. So we're basically looking for P2, the final pressure of a gas with initial volume 7.5 liters. V1 equals to 7.5 liters. Okay. Initial temperature is minus 273. So T1 equals to minus 23 degrees Celsius. Of course, we have to convert it. That is plus 273. Minus 23 plus 273, that's going to give us 250 Kelvin. And then P1 here, initial pressure is 20 atmosphere. 20 atmosphere. Okay, we'll told to look for the final pressure. If the final volume is 15 liters, V2 equals to 15 liters. And of course, T2 equals, final temperature is 27 degrees Celsius. So that's 27 degrees Celsius plus 273. If we add this and this, you get 300 Kelvin. So using your equation of state, P1 V1 over T1 equals to P2 V2 over T2. Here we're looking for P2. So this moves here. P1 V1 T2. T1 remains here. This is coming here. V2 equals to P2. So that way my P2 equals to, what is my P1? 20 atmosphere times V1 here is 7.5 times T2 here is 300 Kelvin divided by T1 here is 250 times V2 here is 15. So when we compute this, we'll be able to get our final pressure. Give us 12 atmosphere. That is P2, simply because the pressure here is in atmosphere. This will also be in atmosphere. So that ends question 3. Let's take a question that has to do with collection of gas over water. So moving on to the next question, we have a question here that talks about collection of gas over water. We have 200 cm cube of an insoluble gas. So that means V1 equals to 200 cm cube was collected over water at 15 degrees Celsius. T1 equals to 15 degrees Celsius. And of course, we have to convert to Kelvin. That makes this 288 Kelvin. and 745 millimeter mercury. P1 here equals to 745 millimeter mercury. If the saturated vapor pressure of water at 15 degrees Celsius is 30 millimeter mercury, if the saturated vapor pressure of water at that 15 degrees Celsius so is 30 millimeter mercury, what this means is that I cannot use this as P1. You see the 745 that I have here, that is my P total. P1 here is not 745 because it says insoluble gas was collected over water at 15 degrees Celsius and 745 millimeter mercury. If the saturated vapor pressure of water at 15 degrees Celsius is 13, so we need to remove the saturated vapor pressure of water here, and that is the 13 millimeter mercury, so that the pressure of the dry gas is 745 minus 13, that is 732 millimeter mercury. Of course, we've interpreted that. We were told to look for the pressure of the dry gas. That's exactly what we've done here. The A part of the question. Volume occupied by the dry gas at STP. You're looking for V2 at STP. P2 is going to be SP, and that is 760 millimeter mercury, whereas T2 is going to be standard temperature, and that is 273 Kelvin. So this is what we need to solve. So the real deal here is that when you collect a gas over water and you're given a total pressure of 745, you cannot use the 745. You have to remove the pressure of water, that's the saturated vapor pressure of water, from the total pressure here to get the pressure of the dry gas, which you are now then going to use in the equation of state. So volume occupied by the dry gas at STP, obviously P1 V1 over T1 equals to P2 V2 over T2. What this means is I am looking for V2. So since I am looking for V2, what I am going to have is that P1 V1 T2 divided by T1 P2 equals to V2. So what this means is V2 equals to, what is P1? P1 is 730. P1 now, this is my dry gas. This is what my P1 is going to look like. 732 times V1. V1 is 200 times T2. T2 is 273. 273 all divided by T1. T1 here is 288 and P2 is 760. So computing this, we are going to get 182.6 cm cube. So that is how we deal with this. And with that, we've come to the end of this lecture talking about general gas equation, otherwise known as equation of state. Do not forget, this is the place to be to ace your next exam. And with that, we've come to the end of this lecture on general gas equation, otherwise known as equation of state. And with that, we've come to the end. And with that, we've come to the end of this lecture on general gas equation or change of state. Do not forget, hit the subscribe button, turn on the notification, and do well to share with your friends. From myself and the team here, it's bye for now.